Swayam Prabha. Digital India. Educated India.
So, in the last few classes we have talked about shrinking core model, right? Yeah, shrinking core model is one of the models which we have discussed earlier, and the other model is homogeneous model. Okay. So, here the imagination is that we have a single particle, but it is highly porous particle, right. So, that means gas can easily diffuse through the particle, and then the reaction is going on throughout the particle. There is no core which you can really identify there. In the previous shrinking core model, there is a clear boundary between the reaction zone and unreacted zone. That is why we call that one as shrinking core model, because the core which is not reacted is slowly shrinking and finally it disappears. But whereas in this model, because it is a highly porous particle, gas can easily diffuse through the pores, and at any time if I look into the particle, this particle is completely occupied by reactant A with the same concentration. If outside concentration is CA0 for example, the same concentration is also there throughout the particle, and if you ignore the film resistance, that is definitely true, right. Film also is not contributing. So, we have a lot of pores. So, then all the molecules of A can go inside and occupy the pores, and then they simply stay there, right, because they stay there and there are reaction conditions. So, continuously the reaction is going on. So, how do we picturize this in our mind first before writing the equations, right. So, we have a particle, porous particle, something like this, then we have reactant B here, reactant B, and after some time we have the same size particle. We are talking about constant size, but now this concentration will reduce, then after some time same particle, the concentration is almost nil, concentration of B I mean, only product you will have. So, with time, this is time t equal to 0, sometime t large T, good. So, as usual, and we are neglecting film. So, that we know if it is film control, we already know how to develop the equation. The same equation can also be used here, whether shrinking core model or homogeneous model, right. If only film is controlling, so then the same model can be used, right. But if it is that there is no diffusion here, diffusion control here, diffusion through ash layer, because I have large number of pores or large size pores, so that the gas can easily enter into the particle, and then the reaction is going on throughout the particle. Good. So, if I want to plot the profiles here, profiles of what? Profiles of solid. Okay. How the concentration of B is changing. So, here at time t equal to 0, you may have here CB0 at time t equal to 0. This is throughout same, no. So, that is why horizontal profile throughout. Okay. This is complete particle we are drawing now, it is okay. Yeah. So, then if it is truly homogeneous model, this is CB0, that means everywhere supposed to be CB0 throughout. So, after some time t, what do you expect? Yeah, I mean not 0 here at this point, yeah, you will have something below here, this is CB profile, and after some time it will still go to less, and CB will be 0. So, that is how the profile decreases, right, because number of moles here are more, then if I take here number of moles which are spread throughout is less, and here number of moles again throughout spread is almost 0 for B, because B would have already reacted, and the reaction is same reaction what you have been thinking. What is that? A gas plus B solid going to products. Okay, good. So now what is what kind of profile you get for A? A is the gas. So if I draw those profiles here, okay, yeah. Yeah. So A, how do you imagine A profile? Huh? In all the cases, it's because I have sufficient amount of gas diffusing and then staying there. It is reacting continuously, and continuously again it is entering, because you know that when immediately concentration is less there, and this gas goes there. So continuously it is always, it is as if you have immersed this particle in a concentration of Ca naught. You have lots of A there. So that is why you will have Ca naught same here. If I take that one as Ca naught, again here Ca naught, again here Ca naught with time. So now with this we should be able to imagine what is the rate of reaction for us. Okay, good. How do we do that? In this case, I think we know that now the rate should be proportional to concentration of A and concentration of B. Okay. So earlier case we took the concentration of B is so large that is why it's not it's 0 order reaction. So it is not directly coming. We are talking only with respect to A, first order and all that. But even here, because the rate is proportional to concentration of A and concentration of B, concentration of A is always constant, whereas B is changing, right. So we can write that as okay, here I write rate of consumption of B is proportional to concentration of A bathing the particle multiplied by amount of B unconverted. Correct? No, already converted one will not participate in the reaction, no, unconverted. Good. Okay. So if I write, we can write also this one in terms of Cb, or we can also write in terms of Xb. Xb is the conversion, which you are already familiar. So if I write this one as the change dxb by dt is this proportionality constant, I will write something Kr, reaction rate, and Ca naught, which is constant throughout, and 1 minus Xa, sorry, 1 minus Xb. So if I take this as equation 1, this will be equation 2. Can I integrate this equation? This is very simple, no, because it is concentration of A and concentration of B left. Okay. Yeah. So 1 minus Xb, and if you the simplest integration, and then the integral expression for this is 1 minus Xb equal to exponential of minus Kr Ca naught into T. Which one?
Amount of B unconverted. Cb naught into 1 minus Xb would be the amount unconverted.
Same thing here also. Left side also I have Cb naught, so it gets cancelled. Yeah, same thing. This Xb also will be there, right? So the definition only I have differentiated this side. So you can write the same thing and then you will get cancelled. Okay, good. So this is the simplest equation. You see now this equation, simplest equation to calculate time, and also it is related with x b. It is simply like your homogeneous reaction. In homogeneous reaction, assuming that this is pseudo, this is almost constant throughout C A naught, that becomes a pseudo first order here with respect to A, and it is not always true that I should have 1 minus x b. I can have in fact x b to the power of 1 minus x b to the power of n. Okay. So, what you do with all this is that once you conduct the experiment, and if you know initially it is a porous particle and a truly homogeneous model may be valid there, that the physical condition of the particle which because you are conducting the experiment, right. So, once you know that, then we have to find out whether it is really first order or second order or whatever order, and you should see that the concentration of A throughout the particle is same for long time, because without any change in that. So, if you have those conditions, then this is the equation I have to try, but still I do not know whether it is first order or second order. So, then I have to imagine this nth order and then try to plot my x b versus t, and then see whether I get a straight line for first order, if not square, then second order. This is called integral method. Okay. Otherwise, you can take the data like this and then put as x to the power of n. Again, you have to plot on log sheet and then try to find out, that is a differential method. Okay. Try to find out what is the order and then correspondingly fit it, right. And here the imagination is only integer orders, maybe one first order, second order, it may not be. So, that is why if you are able to get the data for dx by dt versus x b, better thing is differential thing, you can use differential technique and then try to find out what will be the order of that particular reaction. So, once you are able to fix here it may be 1.5, correspondingly we have to integrate that and then find out the relationship between x b and then the time. What is the ultimate aim in the design? I should be able to tell that how many hours if this particular particle or particles must be there in the reactor, for complete conversion. Okay. And for most of these solid particles, we wait till complete conversion occurs. Okay. So, that is what is the ultimate idea, and this is one of the simplest models in gas solid non catalytic reactions. Simplest, because we have taken here first order. Good. So, now as per our discussions all the time earlier, that we need information for the reactor design. This plot again I am just diagram. This is input, output, we have here kinetics, here we have contacting, here we have physical, chemical, here we have MF, okay, let me write PF and MF. Okay. This is the diagram we have been talking. So, now with all this discussion now for non catalytic reactions, we are supposed to be experts in this now. That means, given any reaction, you know how to find out the kinetics. Kinetics means how the reaction is taking place with time and what are the quantities or what are the parameters that you have to evaluate. If it is shrinking core model with 3 controlling, film controlling, acid diffusion controlling and also reaction controlling, you have 3 coefficients there. You should know Kg and you should know dE, effective diffusivity, and still you should know Ks. And all 3, when you are able to evaluate from the experimental data, then you should have the relationship between x b and then time for a single particle, right. So, that is what is the kinetics will tell us. Now, we have to put that information here, and because you are already experts of this contacting, you know that when you have to take mixture flow, when you have to take plug flow. Now, these two have to be combined to finally get the output. Input is given by demand, market survey, right. So, how many tons of particles you want to process, or how many tons of gas you want to process, if you are interested only in the gas phase, even in non catalytic reactions. But most of the time non catalytic reactions we are interested only in solids, like because combustion, gasification, leaching, and extraction of ores. Leaching is extraction of ores only. Okay. So, in all these most of them are metallurgical reactions. Okay. In process metallurgy, they will be touching like this, but not thoroughly like us, they do not discuss. For example, in blast furnace, right. So, when you have that non-catalytic reaction, you should be finally able to design the furnace, so that you will have 100% conversion of iron ore to, that comes from this information, kinetics. And because you are taking blast furnace, then you should be able to visualize in blast furnace whether I have plug flow or mixed flow. So, that is why now the question is the design of, we will go to the design. I think this is where I stop with respect to kinetic models, right. We have done the shrinking core model with 3 controlling and individual controlling also. So, we have also done, that is for constant size particle. For changing size particle, we have done again one model, right, and this is the homogeneous reaction model, and this particle is not changing. Okay. If this is also changing, but porous particle, what kind of model you use? Just try to extend what you have learned till now. Is it possible to do, or it is not possible for you to do now, because we have not done all the models. We have type A, type B, type C, type D, type E, type E and type F. Okay. 6 models of, we have 6 type of categories. Out of this we have done type A, type B and also type D. Type B and type A together we have done it, and this is type D, earlier gasification and all that what we have done. So, 3 plus this homogeneous. The other things are gas reaction, straight away giving you the solid product, that we have not done, and some other variations we have not done. Good. Yeah. So, if I have for example, changing size, this is not constant, this becomes a little bit smaller, this becomes a little bit smaller. Okay. Is it difficult to handle, or what actually, do you have that information? Just think. I hope question is not confusing, you know. The first thing generally students say is that sir, question is not clear. Okay. Once more. Okay. Yeah, here we have taken this as a constant size particle. Size, here is not shrinking core, because there is no core. No, you cannot use shrinking core model, because it is highly porous model. There is no core. Where is the core? Throughout the particle reaction is going on. There is no clear boundary between unreacted and reacted zone. When you have that boundary only, then you will have shrinking core model. Okay, remember, you know, when you are taking this gulab jam, what do you call gulab jam only? Rasgulla. Yeah, if it is not properly cooked, you will see inside unreacted core, some hard material, right? Yeah. So, then you have to now chew it slightly more difficult, otherwise it will simply melt in your mouth if it is properly cooked. That is shrinking core model. Okay. Even rice also, if those people are very angry with you and they did not properly cook, then outside will be soft, inside will be slightly hard, then that is also shrinking core model, rice cooking also. Okay. So, unless there is a clear boundary between cooked and uncooked, you cannot have shrinking core model. This is a porous particle, but what I am asking is, this is changing with time, the size is changing with time. Do you have any difficulty in handling that? What is saying? No, I am just asking you to extend your thinking, I say, do not just sit there as statues.
There is no film, only.
There is no film, let us not take that film. I am only talking about particle becoming smaller and smaller. Do you have that information?
Same.
Ash layer will form up.
There is no ash layer, no, everything is becoming, see again ash layer comes if you have the, reacted core separately and then product separately. Here product is distributed throughout. When the reaction is going on, product also is distributed throughout.
Average concentration inside the pores.
Yeah, it is actually very difficult, because now particle is shrinking now, you do not know how many moles have been with the time. Yeah, the size is shrinking, but generally you can just imagine, the question itself may be stupid, because what is the reason for shrinking?
Two different particles is if you two different particles.
Why I should use 2 different? We are talking about one particle, I say.
Suppose the particle size was uniform.
That is fine. Yeah, if I have 2 different size of particles there, distribution of particles, each one I can deal with separately, right? That is not a problem. That is a design problem. What he is asking is, I have taken 1 centimeter particle, 5 mm particle. Both are both are homogeneous models. Okay. So, then it is not a problem, because I will design which takes the longest time and then wait.
Shrinking core in a porous particle, is it similar to the pores of a same size particle being filled?
Repeat again. Shrinking core
In a porous particle, is it similar or analogous to a particle of constant size, porous particle, wherein its pores are filled completely?
But in shrinking core, the diffusion regime where you have pores is unreacted core. Is inert core. Shrinking core model you cannot bring at all here, because shrinking core is porous particle.
Shrinking size actually. Shrinking size.
Shrinking size, yeah. Shrinking size, there is no ash around the particle. Okay, yeah. But here we are not saying that. I think this particle is only decreasing by size. But as I told you, question itself would have been stupid, because what is the reason for shrinking, you have to also ask.
If we have for a catalyst, we usually know the surface area per unit mass of the particle or the catalyst. In this case, if we assume that the size is shrinking uniformly, we can calculate the volume and therefore the surface area of the pores which are getting destroyed.
Area.
Yeah. Area of the porous particle. In that case, we can actually, like he was saying, that we can compare it to the deactivated catalyst model. Can we do that, or is that too difficult as well?
Deactivated catalyst, where the deactivated catalyst is almost same. In fact, the similar model used for deactivated, because the deactivation, all our catalyst particles are porous particles. Okay. So, that must be homogeneous. So, the deactivation goes here in the reverse way. Here we are converting the reactant into product, but there the entire particle is very active in the beginning, but when during the reaction there is a reason for getting it deactivated. Like for example, I have been telling you the example of FCC. FCC catalyst is highly porous particle, but one of the side products of FCC, fluid catalytic cracking, is very fine carbon, coke. So, that coke will go and then uniformly try to sit here and there throughout. Yeah. So, then the surface area which is actually participating in the reaction is slowly decreasing. That also got exponentially if I assume first order kinetics there. In fact, the same equation can also be used. Okay. So, that is why when the particle is shrinking, I think first of all these particles, what is the reason for shrinking? Yeah, but here throughout the particle it is happening, right? This is homogeneous model.
It was happening throughout the particle, but here it is happening even on the surface.
Yeah, it is surface as well as throughout, but that is not the reason for particle to reduce in size. I am talking about overall particle, there is no core. Overall particle, it is possible only when you have the total molar volume increasing or decreasing. I think already I told you this one for calcium carbonate. Okay. When you have calcium carbonate particle becoming calcium oxide, and calcium oxide is reacting with sulfur dioxide in the presence of oxygen, then you will have calcium sulfate. So, calcium sulfate molar molecular weight, molar density is higher than CaO. Under those conditions, their particle expands, right. And if you have a similar reaction where the molar density decreases, then particle shrinks. Otherwise, we do not have any reason for increasing or decreasing. Why I am telling all this is, even though we simply tell all this, student is very happy to copy all this and then keep it, wait for the examination. But so much discussion can be made, so much thinking can go, right. So, that is why I try to discuss all this. But it was found already most of the time in the models also, that whenever you have molar change during reaction or decrease or increase, that is not affecting that much the overall model predictions. Even if I take this, right, and then I will assume that it is a constant particle. Someone else will say that no, it is a little bit changing. So, he also takes the model and he also develops a model now with slightly changing particle or expanding particle, right. So, under those two conditions it was found that the difference is very less, and Carberry already proved that, right. So, if you are really able to imagine all this after the class is over, when you are preparing for the examination, then you will have lots of ideas. Okay. But if you are treating this only as examination point of view, there is no excitement at all. You see how much time we have now spent on this just to ask, whether the particle is shrinking or expanding, what is happening. Shekhar, you are asking something?
Another way of looking at this may be, if my reaction rate constant is very high, I mean my gas need not have to go totally inside the particle, then the reaction will again happen on the surface itself, and because of which the surface, the size of particle will get reduced.
If the reaction is very high,
if the Ks is very high,
so
in that case my reaction will happen on the surface itself. The gas will not have time to go inside the particle.
excellent, that becomes equivalent to shrinking core model. If the reaction is very fast, but here when you derive this, automatic assumption is that it is rate controlling. What is rate controlling? Reaction is rate controlling. No, reaction. I have large pores where the diffusion is very free, just going inside. Okay. So, automatically when you say homogeneous reaction model, that is only the reaction control, but actually that is also true. When you have very fast reaction, even though I have porous particle, that behaves as if it is a shrinking core model. So, they are beautiful things, and these two are the basic models. Yeah. And in reality you will not have completely homogeneous model. Okay. And that is why actually what happens is you have to draw the profile inside. Okay. Profile inside, and now that model is very complicated, which I am not doing here, because it takes a lot of time, the derivation. Okay. Why it takes a lot of time? Because first of all I have to establish the profile inside. Profile of what? Ca and Cb both. Ca profile, because there is a diffusional resistance for Cb, and that is Ca. So, that is why Cb cannot uniformly react throughout, right. So, at any point here inside, what is the corresponding Ca and then Cb, and then equation is again same. This is no more constant. So, every time I have to find out what is the average conversion throughout the particle, what is the average concentration of A throughout the particle, then I have to integrate. Okay. So, people have already done it, but we are not doing, because I have to do so many things. Actually, we had earlier in IIT Madras a separate course called Heterogeneous non-catalytic reaction engineering. There we used to discuss all those models, but here I have to do justice to many things. So, that is why just giving some information, and then beyond that your thinking. Okay. So, that is the reason, and straightforward, if I take that model where I have homogeneous model, but still it is not purely homogeneous model, porous particle, then I think at least it will take 1 or 2 weeks for me to develop all those. Mathematics is not that easy, it is very complicated model. Okay. And but lot of imagination is required. I think in 70s there was one Wen, Chinese professor in US, I think West Virginia. He was the starting point for all these models. I think, of course, shrinking core model was already done by Aggie Cooney long time back, but a lot of mathematical details of this homogeneous model was given by that Wen. Okay. Unfortunately, after I completed my PhD, I wanted to apply to him as a PDF, but at that time there is no emails, and there is no fast communications. So, I wrote the letter, and letter came back after maybe 2 months later, so saying that Wen has died recently. I think he was young also, maybe around 51, 50, but he has done a lot of work in gasification. You take coal combustion, you take, some of you may be doing gasification combustion projects, everywhere you see his mark, because it seems West Virginia is very famous for coals. A lot of coal mines are there. So, that is why that university was concentrating mainly on that, USA, West Virginia. So, that is why USA has the tradition of doing very good research work depending on the need. Here also we have a lot of coal, we have Neyveli, but we do not have any project till now. We had some project, but not for conversion and all that. Yeah, because that interaction between industry and academics. If you see that old papers, 1967 was, I do not know whether a journal called Industrial Engineering and Chemistry. How many of you know that? Only you know. You also know? Industrial Engineering and Chemistry. I think it was there till 80s or so. Then they changed it to Industrial Engineering Fundamentals, Industrial Engineering Research and Development, Industrial Engineering Product Development, 3. Same issue, same journal. Then after 7 or 8 years, again they went back to, now the current name is Industrial Engineering, Industrial and Engineering Research, I think. It is there now, Industrial and Engineering Research, Industrial, oh my God, I also forgotten. Yeah, Industrial and Engineering Research, now it is available, we are also getting INDCR or something we have. Research they added, but all sections again together. In that journal, when it was Industrial Engineering Chemistry, this when published those papers, the original paper is still with me, because someone gave me that paper. Yeah. So, this is what about these models, and lots of work is going on even now in these models, because this reaction is a very funny reaction. Non-catalytic reactions are really very beautiful reactions, I do not say funny reactions, very complicated reactions, and calcium oxide to calcium sulphate is one of the very famous reactions just for the sake of environmental pollution. Okay. Calcium sulphate is available plenty on this planet. What is calcium sulphate? Gypsum. Gypsum mines are there. Okay. So, that is available, we do not have to produce that. So, this reaction is not famous for that particular one, but it is famous because when SO2 coming from the chimneys from power plants for example. So, you can remove that SO2, capture it with the solid and then make it as CaSO4, and the CaSO4 can be used by someone, or I think you have to regenerate and again use that calcium oxide, and by regenerating what you get is you are not solving the problem, you are again producing SO2. Okay. But the difference between that SO2 and this SO2 is this is more concentrated, what you are again regenerating. So, that SO2 can be sent to which industry? Sulfuric acid industry. So, that is the reason why it is a very famous thing, and many power plants and all that have been doing it, and the reaction is not that simple. I have told you once that calcium sulphate plus not calcium sulphate decomposition is easy, calcium sulphate decomposition, but calcium oxide reacting with SO2 in the presence of O2 is not that easy reaction. Again I am repeating, because molar volume is increasing there, the pores will block. If more the faster the reaction, then pore closure is faster. So, that means sorry, if I have this is the particle, if the reaction is very fast, only this outer layer will be completed, that will become CaSO4, because it is large in size, I mean the molar volume is large, all the pores are blocked. So, SO2 cannot diffuse inside, SO2 or O2 cannot diffuse inside. So, all this one is unreacted calcium oxide. So, that means you are now producing a lot of solid junk. Environmental problems are wonderful problems. Okay. So, then how do you avoid that? You have to now what you have done is your air pollution problem, you have made it as a converted into solid pollution problem, right. So, that is why people in Germany, I saw that in Lurgi, they used to break this particle, and then after breaking, simplest way of breaking is to putting water, spray water in that during the reaction. Calcium oxide reacting with what is highly exothermic reaction, calcium hydroxide, highly exothermic, it is bubbling actually. I have seen with my own hands in our villages when we are doing whitewashing, once in a year you do for that pongal and all that at that time. So, we used to bring the raw calcium hydroxide, calcium oxide, and then pour water, and you make as a simple as a small bowl like this, and then put that pour water bubbling, it will be bubbling. So, that is why that reaction, and the modeling also is very difficult. The reason is that your idea is to predict when the pore is closed, because beyond that it is useless. So, that is why a lot of work, wonderful work is there on this. I think one Bhatia from India only, but all our people will work only in the US, not here. So, this Bhatia, I think he was in US and then he worked there, wonderful models they have produced. And process control people, do you know there is a professor called Perlmutter? Heard of them? In control and all that. Yeah, this Bhatia worked with that Perlmutter and Bhatia, they have got these papers. And at that time, the specialization means Perlmutter is also specialized in process control and all that, but still they used to work in common chemical engineering problems like this diffusion reaction problems, distillation, absorption, all these problems. So, everyone is expert there, but here now I think we are expert means we do not know anything else, only that part I know, absolutely no connection there. So, that is why when I think in the same building this bench CEO, someone has come from Germany, this auditorium just below us, ICNSR auditorium, he was giving that lecture and then he was telling even in bench company also this expertise has come, it seems there, that the people say that no, I am only expert in back left wheel, I do not know anything about all other 3 wheels, that is all, back side left wheel only his expertise, you do anything with the other parts, he knows only about that. He was also telling that, maybe jocularly or I do not know that, but that is what he was telling, it is so serious about our expertise now. So, I think there are wonderful books also by Perlmutter and all that in our library on process control and all that. Okay, anyway, good. So, our next job is using all these kinetic models, how do we now design the reactor? Okay. So, what kind of reactors we can have, like for example, the reactor means we have reactor design in the form of either plug flow or mixed flow, that is all. Whatever reactor you bring, we can convert that into either plug flow or mixed flow, ideal reactors. Non-ideality will come later, that we have to see when non-ideality is taken into account. Yeah. So, here we will write design of non-catalytic gas solid reactors. Yeah. The factors affecting design may be, I think I have to write here, okay. Factors controlling design. One, we have reaction kinetics. Size distribution, of particles, and number 3, flow patterns of phases, these 3. Do you have information on all these 3 for the design? That means, do you know anything about all these parameters? Reaction kinetics, do you know any information? Now, at this point of time to you I am asking. Huh? What's that? You don't know? Stupid question, huh? Yeah. So, you know, definitely you have learnt, but I think I do not know everyone learnt or not, that is why I am saying that. Okay. Reaction kinetics, we have some information, like what? You can use either shrinking core model or homogeneous model or very complicated models also, which we have not done. Okay. Good. That information, I say, knowing information in any course at the end, you should know some information. It is not that you are, I am asking you to remember the equations, but at least you should know. The moment someone asks you, okay, can you design a non-catalytic reactor, then like a reel it has to go, yes, first kinetics, then what are the models, and then contacting, what kind of contacting possible, right, how the particles move, how the gas move. So, all this they should reel, I mean move in the mind as if it is a reel, continuous reel. So, once you know that information, then getting the details, okay, kinetics, which model is the best, either shrinking core or homogeneous, okay, or in between. So, you know that information and details you can get from literature. I am not asking you to remember all that, but anyway definitely in this course you have to remember till the exams are over, you know those equations. I am not allowing you to copy, or I am not allowing you to bring the notes and all that. So, you have to remember that. Okay. So, that is why kinetics, you know, you have some information, and flow patterns we have discussed already, but still for continuity now I will discuss some more things. Okay. You know already we have discussed, and size distribution of the particles we have not discussed it till now, because we have only talked about single particles. Okay. So, now what we do is, if I have this one is 1 centimeter particle or 500 5 mm particles and 1 mm particle, all three together. Okay. Design is not that difficult when we have that, average you have to take. Okay. So, what is the conversion in the 1 centimeter particle, conversion in 5 mm particle, and conversion in 1 mm particle. So, you have to just average it out, weighted average. In fact, 20% may be your 1 centimeter particles, maybe another 40% may be your 5 mm particles, and 40, okay, another 40 may be 1 mm particles. So, that is why that also is not difficult for you, you can easily handle it. Okay, good. So, if you are talking about contacting pattern now, for non-catalytic reactions, generally what kind of reactors used? Do you have any names in your mind? See, non-catalytic reactions, can you say first of all what are non-catalytic reactions? Iron ore, for example, okay? That is one of the easy things to remember. So, which reactor is used? Blast furnace, that is only one, nothing else. Huh? Rotary kilns are also used. Okay. What is the difference between blast furnace and a rotary kiln when they get the product at the end? Blast furnace, you don't remember at all. This is high school question, I say. High school you should have studied blast furnace, no? No? So, what is the product you get? I mean, liquid metal or so you know why it is called pig iron? I mean, why it is called pig iron?
Sorry.
What is the relation between pig and high oxygen content?
Carbon content.
Okay. Even carbon content, what is the relation? How do you relate pig with carbon? Tell me. Yeah, someone was telling me, I don't know whether it is true or not, but one metallurgist told me, when I asked, sir, what is this pig iron? Not now, I think maybe 15, 18 years back or so. So, he was telling me that when liquid metal is moving, after liquid metal comes out, it moves in the channels. So, when it is moving, that it is highly viscous. So, it forms this kind of boundary and then moves. This is channel, you will have like this, and then it is moving. When it is moving, it looks as if it seems very fat pig, how it walks. You are looking from the top. This is beautiful, very smooth surface for the pig, very nicely. I have seen pigs also. So, maybe you would have not seen. So, beautifully walking, and then that moves as if it is like this. So, that is why we call it as pig iron, he said. It's very nice, I don't know if the story or maybe true also. Okay. So, but you get the liquid directly there, then you can directly put it in the form of rods or in the form of plates, all kinds of things you can do it. But whereas here in rotary kiln, it is solid. Okay. You know what is the name of that product called? Not clinker. Clinker is put, you can also use that kind of thing and wash your body, not soap, sponge. You heard of sponge iron, no? Yeah. Why it is called sponge iron? It is not soft like sponge. It is porous. Porous. So, what you get is sponge iron in rotary kiln. Not only in rotary kiln, fluidized beds can be used. Fluidized beds also can be used, right? So, that is why we have the equipment For example, maybe it is a blast furnace, Yeah, here we have the gas and here we have solid. This solid contains iron ore plus that slag what they put calcium carbonate, yeah, and also they put coke they put. So, all it is a solid reaction there, right. I mean that coal will become that coke will become CO, that CO will be reacting with that. Okay. Yeah, and yeah, this is how it looks. Then you may also have this is rotary kiln. Maybe gas you can send like this, solid like this, solid, gas. Okay, this will be rotating. This is too slant. In fact, you will not have this much slanting. Yeah, nice. Okay, this is the one. Other reactor also we can use this fluidized bed. This is gas. These are the solids. You also have what is called bubbles here. And solid continuously, gas goes out. Okay. And that solid is nothing but your iron ore. Okay. But only in the blast furnace you will have solids iron ore plus coke, and for making that slag I think you add calcium carbonate, I think, or calcium oxide you add there with that. Okay. But here you do not have to add all those things, it is simply Fe3O4 plus CO2 or H2. You can, this gas can be either H2 hydrogen or CO carbon monoxide. I think we have written that, you are looking at me as if you do not know that reaction at all. Fe3O4 plus CO or H2, okay, giving us the product. Yeah. So, these things, and this will tell me what kind of contacting patterns I have. Like for example, quickly going through in blast furnace, what kind of, there are two phases now, okay, till the iron iron becomes molten here only at the bottom here, till here almost you will have only solids moving. Okay. So, and gas may be going this, they blast the gas, that is why I think this is called blast furnace, sides also, bottom, slides and all that. Okay. Yeah, of course, not through liquid iron, but slightly above they put it and then it will go. So, how the solids are moving, how the gas is moving, solids and gas. How means whether it is going as if it is plug flow or as if it is mixed flow. And you know the height of blast furnaces, normally very tall, 5-storied, 6-storied buildings, blast furnace heights, yeah, very big, very large. Yeah, how the solids move? Are they in plug flow or how gas moves? Is it in plug flow or mixed flow? Imagination I say, Narasimha, which one is mixed flow? There are two, gas or solid? Solid in mixed flow. Why? Even if you say plug flow, I will ask why. So, that is why I think why is a very, you have to give the answer. Satyam? Just imagination, I have a large building and where I am slowly pouring that solids, and then finally I get liquid somewhere down here. But of course, reaction may be going on till that point. Yeah, how the solids are moving? You can do all these experiments. I say you can go your home and then take pulses like green grams or something, and put in a funnel and open the funnel slowly. How that moves? Plug flow. Very simple imagination. Unfortunately, that imagination also we are not able to create in your mind. I do not know it is our fault or you have totally insulated brain. Okay? Nothing can go in, nothing can come out. At least black holes are better. Black holes radiation comes out, it seems. But here nothing can go. The perfect insulator is our mind. If you do not want to listen, nothing can go. Correct? No? Really, if something if you want to avoid, 100% efficiency only this. There is no other system which can be so efficient there. Okay. So that's why it's simple imagination only. It's not at all difficult. I think I don't know why you are not able to tell. Okay, gas plug flow. So that is why when I have here, mixed flow. Now understand my idea. I will tell you why you cannot use mixed flow. The reason is definition of mixing itself. Okay, a particle which is here, any instant of time can also come here. Okay, and that particle can also go here, anytime. Is it possible in a blast furnace to have that kind of flow? Never. And by the way, what is the size of the particles they use in a blast furnace? Guess. 1 kilometer to any size. Yeah, that is very good guess. 4 inches. 4 inches. And that is why they have the pelletization plants. Okay, so they cannot use simply very fine, because during mining they get also a lot of powdered ore or small particle ore, and because it is blast, so much gas is going inside, blasted inside. What will happen if you have fine dust or small particles? All of them will come out. They will be thrown out. Terminal velocities. Okay, yeah, that is where I think when I was handling this B.Tech lab, I was asking the question, tell me one use of terminal velocity in industry. 4 or 5 years no one told, of course I only told them later. Yeah, because beautifully we derive equations, Stokes regime what should be the one, and other turbulent regime what should be the one, terminal velocity and all that. But I think definitely we do not know where to use. Okay, but you have not only here in atmosphere terminal velocities, how the dust falls on you. Okay, it goes into the air, and then when there is no sufficient wind to carry it out, then slowly they attain the terminal velocity and fall on you. That is how your cars, your people like me, this surface, all that will be dust. Yeah, so then you have to wipe it out. So I think our cars you just leave, or your motorbike or your cycle, you clearly clean it one day and then wait how many days you will get 1 micron thickness, 2 micron thickness, 4 micron thickness. Okay, yeah. So these are the examples, but otherwise how do you relate what you teach? I say you are not asking anyway, but at least I have to tell, no, and you are interested whether I give this question also in exam or not. That is what only your interest. Okay, good. So what about this one? Gas is plug flow.
The other blast furnace.
This one, yeah, gas is plug flow. That is. Oh, yeah, gas is plug flow. So I wanted to answer is mixed flow and wrote mixed flow there. This neural network also sometimes won't work, I say. Okay, many process control people use neural network, but with wrong learning sometime. Okay, good. So that is the one. And what about this one? Solids are continuously fed here. This moves slowly. Don't think that it goes like your the other one. What is that? Washing machine is very high, but the other one where you sit and then go. Merry-go-round. Yeah. Merry-go-round. Okay, merry-go-round also, if you go to centrifuge velocity, you will go horizontal. So if you make any mistake, you will land somewhere. Okay, so it's very easy. Have you enjoyed that? Good. All of us would have done that recently, not when you are a kid. No, that's why I think as a kid only you enjoy many things, I say. After writing that entrance examination, whether it is JEE or whether it is Andhra entrance X, what is that? M set, K set, R set, S set, all every state has one set. After that we become, I think, very serious without learning anything. Because I think particularly engineering, I think medicine education is 1000 times better than engineering education is. A person who has studied medicine comes out, he will know how to treat at least, but we don't know how to even lift a pump, how to carry a pipeline, how to tighten a bolt.
Their work is not very difficult. If you go to doctor, first he'll ask everything, what are you feeling? According to that, he'll give medicine. He's not going to check out whatever you have.
Oh my God! too simplification I say. So, I will tell a headache, but then if you give something diarrhea tablet to me, so then you should understand, no, you should relate. He says that whatever you say, and then he listens and then writes the thing. To write that medicine, you should know what is the disease, no?
There are three, like summarize, like some antibiotics, there are three. Wherever doctor you go, they give first antibiotics, some they give some.
That is standard, basic medicine always.
Anand needs to appreciate chemical engineering. That we are diagnosing reactors which are not speaking.
Yeah, because this is much more difficult. Veterinary doctors are much more difficult because they cannot ask dog where do you feel pain. So what you have taken today morning?
So the dog owner will speak for the dog then.
Dog owner, but how it feels, how dog owner tells. Feeding he can tell. What you fed to that fellow, he knows. But how it is feeling, it is a problem, no? So that is why I think somehow we are not able to, do after our degree is over. We are not competent to do anything. I am not degrading anyone, but that is the kind of engineering education what we have. That is why one proposal is that finishing school. You take the degree, but afterwards 1 year you work somewhere very seriously in a workshop, learn all this, and then only your degree will be given. Some countries do that professional exam at the end, but we don't do anything here. Okay. Anyway, I think I will quickly tell here. This one, solid is in plug flow, gas is in mixed flow. Oh, sorry, in plug flow. Both are in plug flow here also. Okay. Yeah, here. Yeah, gas is mixed flow, but solid is in mixed flow. Gas we don't know how it flows, but simplest assumption is it can be in plug flow. So then definitely you know why it is mixed flow, because in fluidized bed all these particles are held up or floating in gas, and then these bubbles are there where they go vigorously up and then break. When they are breaking, solids can jump up and then again fall. So when they are falling, they will go anywhere, and that is how you will have almost perfect mixing. RTD also you can do that and then find out it is almost equivalent to plug flow, mixed flow. Okay. So that means a particle in the fluidized bed can move anywhere, anytime. That is the definition of perfect mixing, and that is true in a fluidized bed. You see now, if I am concentrating on solids, assuming that gas is not important for us, then I should use here plug flow for solids conversion or solids for solids, and here also plug flow, and here I have mixed flow. So in the next class we will derive equations for assuming solids in plug flow. What are the kind of equations we get for the design? Design means finding out what is the volume of the reactor. Okay, that is what we want to do in the next class. Okay, thank you.